During our discussion of atoms, we did not spend much time talking about the nucleus. So let's take some time and learn about this very small, very dense, positively charged part of the atom. Remember that the nucleus is made up of protons and neutrons. Scientists regularly refer to any particle in the nucleus as a nucleon. Rutherford discovered protons in 1917. He noticed that hydrogen nuclei were released by nitrogen atoms that were bombarded by alpha particles. After analyzing his data, he realized that a hydrogen nucleus had to be a fundamental particle. That is, a particle that cannot be broken down further. This fundamental particle was the proton. Chadwick discovered neutrons in 1932. Scientists had observed a previously undiscovered type of radiation when beryllium atoms were bombarded with alpha particles. Chadwick used this radiation to bombard paraffin wax, which is high in hydrogen atoms, or as we know now, protons. After analyzing the data from his experiment, Chadwick determined that the unknown radiation was a beam of neutral particles with approximately the same mass as a proton. In other words, a neutron. One question that I am surprised students do not ask more often is how can all of those protons be condensed into a nucleus when like charges are supposed to repel each other? This question also baffled scientists until the discovery of the strong nuclear force. Scientists found that a very strong force of attraction exists between nucleons if they are extremely close together. This force is stronger than the repulsive electric force, so even protons that are extremely close together will be attracted to each other. However, as the distance between protons increases, the repulsive electric force becomes larger than the attractive strong nuclear force, and the protons repel each other. Because neutrons have no charge, they serve as a nuclear glue. Neutrons will not repel other neutrons or protons. They only attract other nucleons via the strong nuclear force. The more protons there are in the nucleus, the more neutrons are needed to balance the repulsive electric force. For example, consider that most carbon atoms have 6 protons and 6 neutrons. Carbon is a light element. Iodine is a heavy element. The most common isotope of iodine has 53 protons and 74 neutrons. The iodine nucleus requires more neutrons so that the strong nuclear force is larger than the repulsive force between the protons. When you completed the atom builder activity, you may recall that some atoms you made had unstable nuclei. Take carbon-14 for example. Carbon-14 has 6 protons and 8 neutrons. This nucleus is unstable. Unstable nuclei are said to be radioactive. Radioactive isotopes emit high-energy particles or electromagnetic radiation from their nuclei in order to become stable. Radioactive isotopes have existed on Earth from its beginnings 4.6 billion years ago. As the Earth formed, 4 layers were created. The solid inner core composed mostly of iron and nickel. The liquid outer core, also composed of iron and nickel atoms. The silly-putty-like mantle, and the solid crust. The temperature increases as you move from the surface to the core. Radioactive isotopes are the cause of this increase in temperature. As radioactivity is given off by these isotopes, the energy is absorbed, causing the temperatures to reach extreme levels. Living things are constantly exposed to radiation, but since organisms have evolved in this environment, we are relatively unaffected by the effects of this radioactivity. Overexposure to radiation can be lethal. If you are curious about radiation poisoning, look up information about the firefighters that responded to the nuclear power plant meltdown in Chernobyl. I should caution you that the images will be graphic. Humans have found many ways to utilize radioactivity. Radioactive isotopes are used in the medical field for imaging, like X-rays, MRIs, and radioactive tracers, and nuclear medicine for cancer treatment. Scientists also make use of radioactive tracers to detect how certain substances move through living tissues. One of the most common household uses of radioactivity is in smoke detectors. A radioactive isotope of americium is used in these devices. We will discuss three types of radiation: alpha particles, beta particles, and gamma rays. You may remember alpha particles from Rutherford's gold foil experiment. Alpha particles are a form of radioactivity that consists of 2 protons and 2 neutrons. This is the same composition as a helium nucleus. Either Greek symbol alpha or the symbol for helium, He, can be used to represent these particles. Notice that alpha particles have a charge of +2, as represented by the subscript in the symbol. This is because they have 2 protons. The relative mass of an alpha particle is 4, denoted by the superscript in the symbol. This is because an alpha particle is composed of 2 protons and 2 neutrons. Because of their mass, alpha particles have a large kinetic energy. Alpha particles have the ability to do quite a bit of damage to living tissues, but their large mass, when compared to other types of radioactivity, means they do not penetrate through materials very well. Alpha particles are stopped by a few centimeters of air and are easily absorbed by paper or your skin. For this reason, alpha particles do not pose much of a threat externally. However, ingesting alpha particles is bad news. The soft internal tissues will be easily damaged by alpha particles. Alpha particles quickly absorb electrons from the surroundings to become harmless helium atoms. In fact, all of the helium atoms found on Earth were once energetic alpha particles. Beta particles are electrons. If you think about the structure of the atom, beta particles might confuse you. How do electrons come from the nucleus? I thought electrons were only in the electron cloud. Beta particles are the result of a neutron converting to a proton. Remember that unstable carbon-14 nucleus? Well, if one neutron is converted to a proton, a stable nitrogen-14 atom is created. Carbon-14 isotopes release beta particles to create a stable nucleus. Either the Greek symbol beta or the symbol for an electron, E, can be used to represent these particles. Notice that beta particles have a charge of -1, as represented by the subscript in the symbol. The relative mass of a beta particle is 0, as denoted by the superscript in the symbol. Beta particles will cause an intermediate amount of damage to living tissues due to their relatively insignificant mass. However, this same small mass means that they can penetrate materials pretty well. Beta particles will penetrate air and paper pretty easily, but can be stopped by denser materials like aluminum. Beta particles pose more of a threat than alpha particles when absorbed by the skin. However, just like alpha particles, ingesting beta particles will cause the most damage. When a beta particle is finally stopped, it simply becomes an electron in the substance that absorbed it. If you remember from your electromagnetic wave poster project, gamma rays are a form of electromagnetic radiation. Many unstable nuclei achieve stability by simply emitting high-energy gamma rays. The Greek symbol gamma is used to symbolize a gamma ray. Notice that since gamma rays have no mass and no charge, zeros are used for both the subscript and the superscript in the symbol. Gamma rays will cause a large amount of damage to living tissues due to their enormously high energy. This high energy also means that gamma rays can penetrate materials very well. Gamma rays will penetrate easily through air, paper, and aluminum. An extremely dense material, such as lead, must be used to stop them. Because of their high energy and excellent penetrating ability, gamma rays pose the largest health threat when compared to alpha and beta particles. A final thing to consider is how these different types of radiations would interact with a magnetic field. Remember that moving charged particles create their own magnetic fields, so both alpha particles and beta particles can be manipulated by an external magnetic field. However, since gamma rays have no charge, they will pass straight through an external magnetic field. Notice in the diagram that the gamma rays go straight through the magnetic field. Alpha particles are deflected one way by the magnetic field due to their positive charge, while beta particles are deflected in the opposite direction of alpha particles due to their negative charge. Also notice that beta particles are more affected by the magnetic field, meaning that they curve more than alpha particles. This is because beta particles have no relative mass, while alpha particles have a relative mass of 4. Beta particles are easier to deflect because they have less mass. Alpha particles deflect less because they have more mass. Well, that wraps up the first lesson about the nucleus and radioactivity. In the next video, we will discuss half-lives and transmutations.